The main purpose of grounding is to provide a low resistance path for electrical current to return to the source in the event of a fault. The main disconnect is the point where the utility service enters the building, and it serves as the central point of grounding. By connecting the water ground to the main lug panel, a direct path back to the main disconnect is not provided. Instead, the current would have to travel through multiple connections from the main lug panel to the service cable and then to the meter before reaching the main disconnect. This can create additional resistance and reduce the effectiveness of the grounding system. The National Electrical Code, also known as NEC, requires that the water ground be connected to the main disconnect. This is stated in section 250.24. C4. The grounding electrode conductor for a grounded water pipe system shall be connected to the cold water pipe at the point where the water service enters the building or structure. The reason there may have been a passing inspection in one location and failure in another may be due to different interpretations of the NEC. The inspector who failed the installation may have taken a stricter stance on the requirement to connect the water ground to the main disconnect. To ensure code compliance and a passing inspection, the water ground should be connected to the main disconnect. This can be done by running a separate grounding conductor from the water meter to the main disconnect. The conductor should be sized appropriately for the fault current calculated for the system. The service cable you installed already includes a grounding conductor, which is connected to the grounding lug in the meter and the ground bar in the main lug panel. Separating ground and neutrals in the main lug panel is a good practice to prevent cross-contamination of the electrical system. Ground rods should be connected to the grounding lug in the meter, not the ground bar in the main lug panel. When dealing with electrical systems, ensuring proper grounding is paramount for safety and code compliance. The National Electrical Code, NEC, provides comprehensive guidelines for grounding and bonding to minimize electrical hazards. A key aspect of grounding is understanding the role of the grounding electrode system, which includes elements like ground rods, water pipes, and the grounding electrode conductor. The grounding electrode conductor, or GEC, plays a vital role in connecting the grounding electrode system to the service equipment. The primary objective of grounding is to create a low impedance path for fault current to return to the source, typically the utility transformer. This low impedance path facilitates the rapid operation of overcurrent protective devices like circuit breakers or fuses, thereby minimizing the duration of a fault and reducing the risk of electrical shock or fire. When a fault occurs, such as a short circuit, current will flow through the path of least resistance. A properly installed grounding system provides this path, allowing the fault current to quickly return to the source and trip the overcurrent protective device. Without an effective grounding system, fault current may find unintended paths through equipment, metallic enclosures, or even people, posing significant safety hazards. Now let's address the specific scenario of connecting a water ground to the electrical system. According to the NEC, a metal water pipe that is in direct contact with the earth for at least 10 feet or 3.0 meters is considered a grounding electrode and must be connected to the grounding system. Section 250.52. A1 of the NEC specifies the requirements for using metal water pipes as grounding electrodes. However, it's crucial to understand where and how this connection should be made. As previously mentioned, the NEC requires that the water ground, or the connection to the metal water pipe, be made at the main disconnect. The main disconnect is the point where the electrical service enters the building and typically houses the main circuit breaker or fuses. Section 250.24. C4 of the NEC provides the specific requirements for connecting the grounding electrode conductor to the metal water pipe. Connecting the water ground directly to the main disconnect ensures that the grounding electrode is effectively integrated into the grounding system. This direct connection minimizes impedance and provides a reliable path for fault current to return to the source. Connecting the water ground to the main lug panel instead of the main disconnect can create several problems. Firstly, it introduces additional impedance into the grounding path. The fault current would have to travel from the water pipe through the grounding conductor to the main lug panel, then through the service cable to the meter, and finally back to the main disconnect. This indirect path increases the overall impedance of the grounding system, which can slow down the response time of overcurrent protected devices and reduce the effectiveness of the grounding system. Secondly, connecting the water ground to the main lug panel may not comply with the NEC requirement. Inspectors typically enforce the NEC strictly, and any deviation from the code can result in a failed inspection. The inspector who failed the installation was likely enforcing the requirement to connect the water ground directly to the main disconnect as specified in section 250.24 C4. To rectify the situation and ensure code compliance, a separate grounding conductor should be run from the water meter to the main disconnect. This conductor should be sized appropriately based on the size of the service entrance conductors, as specified in table 250.66 of the NEC. The grounding conductor should be securely connected to the metal water pipe using a listed grounding clamp or fitting. Additionally, it's essential to verify that the metal water pipe is electrically continuous and has no insulating sections or joints that could interrupt the grounding path. If there are any concerns about the continuity of the water pipe, a bonding jumper should be installed to bypass the insulating section. Now, let's clarify the role of the service cable and the grounding conductor within it. The service cable typically contains a grounding conductor, often referred to as the equipment grounding conductor or EGC. This conductor is connected to the grounding lug in the meter and the ground bar in the main lug panel. The purpose of the EGC is to provide a grounding path for non-current carrying metal parts of electrical equipment, such as enclosures, conduit, and appliances. The EGC helps to ensure that these metal parts are at or near ground potential, reducing the risk of electric shock. While the EGC and the service cable contributes to the overall grounding system, it does not replace the requirement to connect the water ground directly to the main disconnect. The water ground serves as a primary grounding electrode and provides a direct connection to the earth, while the EGC provides a grounding path for equipment. Separating the ground and neutral conductors in the main lug panel is a recommended practice. This practice helps to prevent neutral current from flowing on the grounding conductors, which can cause voltage drops and create unwanted circulating currents. By keeping the ground and neutral conductors separate, the grounding system operates more effectively and reduces the risk of electrical noise and interference. Ground rods are another common component of the grounding electrode system. Ground rods are typically driven into the earth near the service entrance and connected to the grounding system. The purpose of ground rods is to provide a supplemental grounding electrode and help to stabilize the ground potential. The NEC specifies the requirements for ground rods in section 250.53. It's important to note that ground rods should be connected to the grounding lug in the meter, not the ground bar in the main lug panel. This ensures that the ground rods are effectively integrated into the grounding electrode system. In summary, to ensure a safe and code-compliant electrical installation, the following steps should be taken. Firstly, connect the water ground, or the grounding electrode conductor for the metal water pipe, directly to the main disconnect. Secondly, size the grounding conductor appropriately based on the size of the service entrance conductors, as specified in table 250.66 of the NEC. Thirdly, verify that the metal water pipe is electrically continuous and has no insulating sections or joints. Fourthly, ensure that the service cable contains a grounding conductor and that it is connected to the grounding lug in the meter and the ground bar in the main lug panel. Fifthly, separate the ground and neutral conductors in the main lug panel. Sixthly, connect ground rods to the grounding lug in the meter, not the ground bar in the main lug panel. By following these guidelines and adhering to the requirements of the NEC, the electrical system can be properly grounded, minimizing electrical hazards and ensuring the safety of people and property. Remember, electrical work can be dangerous, and it's always best to consult with a qualified electrician if you have any questions or concerns. Now let's delve deeper into the technical aspects of grounding and bonding, exploring the concepts of impedance, fault current, and the role of different grounding electrodes. Impedance is the total opposition to current flow in an alternating current circuit. It includes both resistance and reactance. In a grounding system, low impedance is crucial for ensuring that fault current can quickly return to the source. High impedance in the grounding path can impede the flow of fault current, slowing down the response time of overcurrent protective devices and increasing the risk of electrical shock or fire. Fault current is the current that flows during a fault condition, such as a short circuit. The magnitude of fault current depends on the voltage of the system, the impedance of the circuit, and the impedance of the fault itself. A properly designed grounding system must be able to safely handle the maximum available fault current. Grounding electrodes are conductive objects that are buried in the earth and used to establish a connection to ground. Common types of grounding electrodes include metal water pipes, ground rods, ground plates, and concrete encased electrodes, also known as U-for-grounds. Each type of grounding electrode has its own advantages and disadvantages. Metal water pipes are often used as grounding electrodes because they provide a large contact area with the earth and are readily available in many buildings. However, it's important to ensure that the water pipe is electrically continuous and has no insulating sections. Ground rods are a simple and cost-effective way to provide a grounding electrode. They are typically driven into the earth at least 8 feet or 2.4 meters and spaced at least 6 feet or 1.8 meters apart. Ground plates are flat metal plates that are buried in the earth. They provide a larger contact area than ground rods and are often used in areas with poor soil conductivity. Concrete encased electrodes are grounding electrodes that are encased in concrete. They provide a very low impedance connection to ground and are often used in new construction. The NEC requires that all grounding electrodes be bonded together to form a grounding electrode system. This bonding ensures that all grounding electrodes are at the same potential and that fault current can flow freely between them. The grounding electrode conductor, or GEC, is used to connect the grounding electrode system to the service equipment. The size of the GEC is determined by the size of the service entrance conductors, as specified in Table 250.66 of the NEC. Bonding is the process of connecting together all metal parts of an electrical system that are not intended to carry current. This includes equipment enclosures, conduit, metal raceways, and other metal components. The purpose of bonding is to create a low impedance path for fault current to return to the source and to minimize voltage differences between metal parts. Bonding is typically accomplished using bonding jumpers, which are short lengths of wire that connect together the metal parts. The NEC requires that all bonding jumpers be sized appropriately for the circuit they are serving. In addition to grounding and bonding, surge protection is another important aspect of electrical safety. Surge protection devices, or SPDs, are used to protect electrical equipment from voltage surges, such as those caused by lightning strikes or power line disturbances. SPD work by diverting the surge current to ground, preventing it from damaging sensitive electronic equipment. The NEC requires that SPD be installed in certain locations, such as at the service entrance and at branch panels. Selecting the right SPD depends on the voltage of the system, the expected surge current, and the type of equipment being protected. Understanding the principles of grounding, bonding, and surge protection is essential for ensuring the safety and reliability of electrical systems. By following the guidelines of the NEC and consulting with qualified electricians, electrical hazards can be minimized and the risk of electrical shock or fire can be reduced. Always remember to de-energize electrical circuits before working on them and to use appropriate personal protective equipment, or PPE, such as safety glasses and the insulated gloves. Electrical safety should always be the top priority when working with electrical systems.